Welcome to part 2 of inverse functions, and in this section we will learn how to verify that two functions are actually inverses or prove that they're not using composition. We did composition in 5.1, that's f of g of x. We want to know, are these two functions inverses? Well, you could say that instead of using composition, you could just simply straight up find the inverse of f of x and see if it's g of x. Alternately, you could do the same thing with g of x. Swap x and y and do the algebraic process we learned in part 1. In this section, we are showing a more mathematical proof sort of way that these two functions are in fact inverses for all x. It's a way that is a little bit more official, if you will. So what we want to do is we want to compose the two functions, meaning we want to do f of g of x. That means, recall, that we are first putting x into the function g and then putting it through f. Now, if these two functions are in fact inverses of each other, what g of x does to x, f should undo it or invert it. And what should we get back out? Well, what we originally put in. Similarly, we should also be able to go the other way and do g of f of x and get out x as well. This idea is sort of like things we've talked about and you've previously learned in mathematics in previous classes where, like, if you took the square root of x and then squared it, you just get x back out. Squaring and square rooting kind of are inverse of each other. They do the opposite things. Similarly, addition and subtraction, multiplication and division, there are many of those inverse operations in mathematics. And we want to just make sure that what f does or what g does, the other function undoes it. So let's first verify or see if these two functions are inverses by doing f of g of x and seeing that we do in fact get x out at the end. So let's make sure and see. So f of g of x, what we're going to do is plug g of x, 12 minus 3x, into the f of x function for x. So we're going to have 12 minus, and then since we're plugging in all of g of x into the function and we're subtracting, we need parentheses. So here's our g of x function. That's what we're plugging in to our f function, and that's all over 3. In the next line, we'll simplify by distributing the minus sign. Then we can simplify our numerator, and then we can cancel the 3's to see that we do in fact get x out. Now we have to go the other way and compose the alternate direction to make sure that they both work. So this did get x out. Nice. Then we want to make sure that the other way does as well. So we want to see if g of f of x also gets x out. So this is doing g of f of x. So now we're going to write our g function, but to plug in for x, we're going to plug in 12 minus x all over 3. So we will have 12 minus 3, and in parentheses, we'll input our f of x function, so it's 12 minus x all over 3. Now here, these 3's can cancel because they're top to bottom, and so we're left with 12 minus x. There are alternate algebraic ways to do this. You could have distributed the 3 through and done more things. This is just the most straightforward way. So we have 12 minus 12 plus x, and to simplify, we have x. So since composing these two functions in both orders, both outputted in x, we can verify that the two functions are in fact inverses. So here is our conclusion. Since f of g of x and g of f of x both equal x, we can conclude that f of x and g of x are in fact inverse functions. And that is how you verify that two functions are in fact inverses, or another way to say that, one is an inverse of the other, through composition. In this example, we want to verify that these two functions are in fact inverses using composition. So we already have the correct notation, f of x and f inverse of x. So let's say we had this function, We algebraically found the inverse by swapping x and y and resolving for y. We renamed y f inverse of x, and we want to ensure that we did get the correct answer using our algebraic steps. What we can do is verify that f of f inverse of x is in fact x, and then we'll go the other way and verify that f inverse of f is also x. So we need to verify composition both ways gets out x. Okay, let's do this left one first. So to rewrite this, this is really f of f inverse of x. And then instead of writing x here, because we just want to verify this, so we need to make sure that we get x out. Alrighty, so taking f of x, we're going to write out 5 over x minus 2, but instead of x, we're going to plug in f inverse of x. F inverse of x is this entire fraction here. So we're going to have complex fractions, but we can simplify those using algebra. So we will have 5 over, and instead of writing x, we're going to write 2x plus 5 over x, and then the minus 2. So again, I wrote out this function, but replaced x with f inverse of x. Now, in our denominator here, we have one term that's a fraction and one term that's not. So what we want to do is actually get a common denominator, so we can have this as one fraction in the denominator. So our common denominator should be x, so we want to make this 2 a fraction with x in the denominator. In order to do that, what we need to do is multiply both the numerator and the denominator by x. So in our next line, we'll have 5 in our numerator, over, in our denominator, writing this as one single fraction over x, we will have 2x plus 5 minus 2x. Well, 2x minus 2x is nothing, so this is just 5 here. Now, rewriting this even more, when we divide two fractions, we're really multiplying by the reciprocal of the denominator. So our numerator is 5 over 1. That's just the 5 up here. I rewrote it as a fraction. And we're dividing by 5 over x, which really means that we're multiplying by the reciprocal of 5 over x, which is x over 5. When we do that, you can either cancel the 5s straight up here, or if you do not wish to do that, you can see that you'll get 5x over 5 through multiplication, and you can cancel the 5s there. Either way, you end up with x over 1 or just x. So we verified that when we compose the two functions going the first way, we did get x out in the end. Now we need to verify our functions going the other way and verify that we get x out again. Going in this order, this means that we are doing f inverse of f of x. So we're going to write out the f inverse function, which is here. And the f inverse function has two spots where there's an x. So in two spots, we're going to plug in f of x, which is 5 divided by x minus 2. So this one might look a little more tricky. So we have 2 times 5 over x minus 2 plus 5. So far I've written the numerator and plugged in f of x here for x. Then we have the denominator. The denominator is just x, which means I need to once again plug in f of x, which is 5 over x minus 2. Okay, once again, we have a complex fraction. And if I didn't already say, a complex fraction is a fraction within a fraction. Your goal here is to make it as simple as possible. All right, so in our numerator, we can multiply this first part here. This is really 2 over 1, so that's why the 2 only gets multiplied by the numerator of 5. So that fraction there is really 10 over x minus 2, and then we still have the plus 5. All over 5 over x minus 2. Now, like we did over here, when we had the fraction in the denominator here. We wanted to get it like down to one fraction by getting a common denominator. So up here we want to do the same thing. That common denominator should be x minus 2. So we're going to multiply both top and bottom of this 5 by x minus 2. Then we can rewrite that overall numerator, and we'll have 10 plus 5x minus 10 all over x minus 2, and that's the entire numerator. Then divided by, we'll make that a darker fraction bar, 5 over x minus 2. We'll keep going and simplify our numerator and denominator of our complex fraction. So in our numerator, the 10 and the minus 10 will cancel, so we'll have 5x over x minus 2 divided by 5 over x minus 2. Now in this complex fraction, the numerator and the denominator already have the same denominator. Those can actually just cancel. I will show you why that works here off to the side in yellow. So again, we're dividing fractions, which really means multiply by the reciprocal of the bottom fraction. So this is what we have here. Oops, that should say 5x, sorry about that. And then we're multiplying by the reciprocal of the denominator, so x minus 2 over 5. Now you can see why these x minus 2's will just end up canceling either way. So boom, boom, and we're left with 5x over 5, and the x's will the 5's will cancel rather, and we're left with x. So in yellow, that's one way to take a look at it. If you wanted to just go straight up and cancel from this original fraction in black here, I can show you that as well. Kind of like a little math trick. You can cancel them straight up from there, and then you are left with, again, 5x over 5. It's simplified on its own, and once again, we'll have x out. So either way is great. If you like to look at dividing two fractions as multiplying by the reciprocal of the denominator, that's perfect. If you can use little math tricks throughout the way to help you as well, that's awesome too. Either way, we get x out in the end, and so we have verified, that composing our functions both ways outputted an x. Therefore, the two functions are in fact inverses, and we verified by using function composition.